Welcome to Loads in RISA-3D. My name is Debbie Penko. What we'll be doing today is talking a lot about all the different loading options we have in RISA-3D, specifically RISA-3D, and we'll talk about the ways to apply the loads, what kind of techniques that will happen when you do apply the loads, and some of the different things people have problems with their loading. So starting out, let's talk a little bit about each type of load that we'll be discussing today. The first one is going to be joint loading, and it is just like it sounds. That gets applied to a joint, and we'll be talking about the different types of loads you can apply in a joint. We also have distributed loading. That's also known as line loads. You can apply, if you were just to do a hand calc on a beam, that might be what you would do a line load, but we in RISA are talking about it as a distributed load. We also have point loads. Point loads can also be confused with joint loads. Really, a point load is the same as a joint load. It's a single load that can happen on a member, so it requires a member there instead of a joint, but that's the only difference between a joint load and a point load. We also have area loading. Area loading is a really powerful tool. It makes your modeling quick and easy if you have members, but it does just kind of requires a little bit understanding what you're doing there. So we'll take a look at area loading. Surface loading often also gets confused with area loading. So area loading gets applied to members. The difference between a surface load and that's going to be on a plate or a wall. So we can apply a surface load to a plate or a wall as a constant pressure, or an area load will be applied over an area on a member, a group of members. So let's see here, the next second to last year we'll be doing some moving loads, talking about how to apply them, and we'll take some examples of that. And lastly, we'll go into a little bit here of automated loads. RISA has the ability to apply wind and seismic automatically to a building design there, so we're going to see how to do that and what loads come out there. So kind of an overview of the loading and how you apply loads. There's a couple different ways to apply loads, and the first way we'll talk about is graphical interface, where you can just apply the loads, just clicking on the graphical interface and then defining that right in the RISA-3D graphics. You can also get to this here by using insert. In your Windows menu here, you have an insert, joint loads, point loads, distributed loads. So basically all the ones we just talked about, all of those can be covered right by using your Windows tool there, insert. You can also see all of the loading. Once you've applied that, you can see them. They get grouped inside the basic load cases spreadsheet. So it allows you to access all of the loads once they've been applied to the structure. And you can see, like, if we look at this in a real-life model, we would see that grayed out one would be clickable, and we would open up into another spreadsheet, or the two. And what those numbers indicate there are that there's one load inside of that, one distributed load in that dead load spreadsheet right there. So you kind of have to look at this in look at the basic load case here that we're looking at, and then you look at the top column. That's a distributed load column. So you click on that, and another spreadsheet would pop open. Same thing in area load. You look at that live load. You could click on that once we're in the program, and then another spreadsheet would open up telling us a little bit more information about that. So this basic load cases spreadsheet is kind of what would be a central hub of all of the loading that you have in your model. So you could always come back to here, kind of see what you're looking at in the model, and this is a great place to understand a little bit more about what's happening in the model. You can also just enter loads right in here in the spreadsheets there. So you can access these blank ones and just enter your loads right into that instead of graphically into the spreadsheet. So the other way to get into the spreadsheets here is on our data entry toolbar. So we see that basic load cases spreadsheet. The data entry toolbar floats around on the right side of our screen, and what we can do is click on the basic load cases spreadsheet here, the moving loads, the load combinations. Those are the three loading options that we have on the data entry toolbar. About a couple years ago, it was more expanded, and we kind of ran out of room and decided to take it out, but some folks wanted it back. So what we've got in there is a preference there. So if you go inside of RISA, there's a tools preference, and you can see that it tells you, show the data entry toolbar loads buttons. So we used to have some other loads in there, and if you click on this and check that box there, what will happen is you'll get those joint loads, point loads, distributed loads, member area loads, surface loads. So all of those are going to be added back to the data entry toolbar. Your data entry toolbar gets kind of long, so when you open up RISA-3D as a default, we're looking at it in the left side here. But if you do want to make this change, you can go to Tools, Preferences, and adjust that for yourself. The other thing is load combinations. So once you've created your loads, I want to put those in combination and apply that to the model. So the load combination spreadsheet is very handy here to build your own load combinations. What you go in and you're going to enter in some of your own load combinations. You can tell the program to use a DL, an LL, a WL, etc. So we're just telling it dead load, and this is basically what we call a load category. So when you're using load categories, all of these different types of things that are coming basically right out of the IBC, then what you can do is you can just tell the program DL with a factor of 1, for example, or DL plus LL special there with a factor of 1 on each one. The important thing is don't forget to use your load categories. When folks are starting to get used to RISA, what happens a lot of times is they use these categories, but they've forgotten to put the categories in their basic load cases spreadsheet. So they want you, if you're ahead you're working in your load categories, in your load combinations, you want to make sure you use load categories if you used it in your basic load cases spreadsheet. So I see that a lot kind of as a beginner. You get confused there. But the other thing you can do is you can just use basic load case as a row number. Instead of telling the program DL, you can just tell the program row number 1 in the basic load cases spreadsheet. So we see here basic load case 1, which is that entire row. Whatever happens on that row, we'll use that in our actual load combination. So we enter a 1 in the BLC with a factor of 1. So two different types of methods. One is to use a category, and one is just to tell the program, use that entire row of information. So if we wanted to get to the second row, we would just type a 2 in the basic load case, and then we would tell the factor of whatever factor happened to be there. So you can just use that as a different method. So those are two methods on building your own combinations. You can also nest your combinations. Lots of times folks run out of room if you're especially maybe in a large type of structure or a maybe industrial structure that doesn't fit the normal IBC type of loading. You can see here what I show here is the gravity loads, show the dead load, live load. We have snow, we have fluid. I have some other load, OL1, OL2. That indicates it's an other load. And that is, I'm running out of space. Basically, I only have 8 basic load cases per the load combination. I'm running out. But what you can do, if you need to add the quartering winds to all these gravity loads and I want them all to be checked at once, what I could do is combine the load combinations by nesting them. And when I nest them, all I'd have to do is tell the program L1, which indicates load combination 1, or L2, which indicates load combination 2 there. So these two are now being added together in this nested example 1. I can also do a combination there of mixing and matching load combinations and basic load cases. So in the second nested example 2, I've gotten L1, L2, and I added an other load 3. So all of that together will be run all combined. You could do all sorts of things. You actually can nest on top of nesting. So you could do a third example where these two are nested together, added together. L4 and L5 gets added together. So you can keep going as needed. This allows you to sort of add everything together. So let's see here, the next one we've got. The other thing to do instead of doing it manually, you can use the load combination generator. This becomes really helpful, especially if you're using the IBC or ACI or any of the codes there that give you specifics versus maybe things that you're doing on your own. So if you have your IBC, this one I'm showing here, the IBC strengths, what you can do is tell the program, was there roof live load in there, was there snow load, was there rain load? Pick out there if you want some notional loads. And you just want to use what you've applied in your model. So if you haven't applied any snow load in your model, it would be silly to make a combination that has snow load, since it's just a waste of time there. So you might uncheck that if you haven't applied any snow load. What this is load combination generator. So you want to make sure you actually have the loads in your model. But once you push generate an entire list there, and we'll see this later on in my presentation. We'll do this a little live so we can see it, but what you will get is it will generate all of the gravity combinations that would apply to this type of scenario. The wind one you can see here. It gives us the ability to do quartering winds with eccentricity. We have X and Z, 2D only. Again, if you have applied that type of loading, make sure to pay attention. If you've done WLX, for example, or WLZ, then you might want to check the X and Z. But if you've just done WL as a wind load, then you would be doing a 2D only. Okay, so make sure you're using the type of loads there that you have in the categories. These are all category-based. The last one is the seismic, and you can see you can choose all the different options. There's a lot more options in here, non-orthogonal. We also have the overstrings combinations that you can create here as well. So you have a long list of automated load combinations for yourself, and we'll see that in a second. Okay, so with all of those load combinations, let's talk a little bit more about applying the loads. So the joint loads is the first one I want to talk about, and the joint loads there you can apply to any joint. We've got some options in here. We look at the dialog that comes up. It tells us it could be a load, and that load there can be applied to a global X, Y, and Z. When we see a capital X, Y, and Z, it always indicates its global axis. Okay, so a joint, since it doesn't have to associate with a member, will always be living in the global axis. You can also apply the moment in the MX, MY, or MZ directions. So that would be a load. You can also apply it in force displacement, and I'll show you an example of that here coming up. But you can apply that with what it'll ask for is the magnitude in maybe inches or whatever your distance happens to be for that magnitude. The last one there is mass, and this might be something used for dynamic analysis, and you can do a directional mass. That might help you if you need. It helps prevent, if you apply mass instead of load, you can maybe identify or prevent the local modes. You can also do mass moment of inertia, and that might help account for the rotational inertia effects in your model. So this one here helps you all for the dynamic analysis. Typically we're going to stay in the load one right now, but what we also can see, let's just take an example of this enforced displacement. So the enforced displacement might be a case where maybe this is a sinking support, a failing footing, or maybe just a repair situation where this is sunk, and what you need to do is find out how that will affect the structure. So what you can see here is you can tell the program that this is a displacement, or D is a displacement, and the direction I've kind of done in this example is it's going to be displacing 4 inches in the Y direction. -4 means it's going to be going down. So if we kind of just see once I've actually ran that model, this is just an image showing us what the displacement would look like. And we see that it just sort of scoots the whole model down by 4 inches from that original location in there, and then the whole model kind of reacts from there, and the forces distribute from there. So this is a really good tool if you have maybe a repair situation. So I'm going to keep going from there. The distributed type of loading here we also have. These apply to both members and walls, and so we can either do this on a wall. The wall is going to be to the wall panel edge, and if we're going to apply it to a member, it can be anywhere along that member. You can tell the program that you're going to be doing a tapered load, so you can tell if the start magnitude is different than the end magnitude. In this example here, I'm showing that it's going to be a -1 to a -5, so it would have actually been tapered in there. We can also tell the program here to start and stop anywhere. So I see this image here. It tells me, shows I've done exactly this here, this 25% location, and then it's going to the 75% location. So you can enter in feet, or if that's your units there, or you can do percentage, and it will adjust that. If you leave start location and end location blank, it will default to the entire member. So you want to tell the program how you want to apply that distributed load, and then you're going to tell a little bit of the basic load case and apply it to the actual member there. So you can kind of work with a lot of different things in your distributed loads, but specifically for the direction of the load, there's some things here you can do in the global axis. Again, I mentioned a capital X, Y, and Z indicates global axis. A lowercase x, y, and z indicates the local axis. And so you can apply that to the local axis. That might be helpful if we need to apply it. Maybe if we're looking at this one here, the global would be vertically down like we see in the lower right corner here. But if we wanted it to maybe apply a perpendicular to the member, we would maybe use the local y-axis there. And would be perpendicular, or maybe along its length, it would be to the local x direction. We can also apply a torque to the member, so to the local x-axis. We can see if we applied mx, that would just kind of torque it in the, if we put our finger in the right-hand rule, our thumb in the direction of x, we would be torquing around that or about that axis. And then we also have thermal loading. I want to go into some specifics on the thermal loading here in just a second. But the last piece too as well is projected loading. And I want to show you guys some specifics on how you would figure out your projected loading. So let's take a look at thermal loading to start. So thermal loading is just like it sounds. It's the effect of the temperature differentials. So if you are applying a temperature, if the structure is going to be going through large temperature changes, it will be causing the axial expansion or contraction of the members. You can apply that directly to the member as a load. So the way you want to tell the program, though, you need to give it sort of a base point or an ambient temperature. What we use here in RISA right now is, as a default, is coming in as 0 degrees. So it's going in at 0 degrees Fahrenheit, and I sort of always leave it at 0, and then I give a change of temperature there. But if we're looking at a specific temperature, maybe we want to leave that at a higher temperature, and then more like a room temperature or where your structure actually happens to be, and then the change in temperature is really what we're applying to it. So it would be what the difference between the ambient is versus where the structure is going to be experiencing. But a good example of why you might use temperature loading more commonly than a structure that's experiencing weather might be pre-stressing the braces. Because as I mentioned, what happens when we apply temperature is it's going to cause axial loading. And so what we can do to a structure where we want to apply some pre-stress or some axial tension load into the member, we can do that automatically by using this temperature loading. So this model in particular shows here what we've got is just a brace frame with some large compressive forces. And as we apply these compressive forces, we want to, maybe we want these rods or cables really to act as tension-only members. But what happens is when we run that model, and I show you the deflected shape, what's happening is that the compressive forces in the columns are actually pushing right into the beams, and that means that those beams are those braces, and those braces are experiencing compression, and they are tension-only members. So the way we can work around that is to pre-stress them so that they don't actually get removed right from the model from the start as the compressive force gets applied. So what we can do, and we want to look at an example here, is we want to examine how much axial force we need to apply so that it really just starts it out at pre-stress level just for gravity loads so that it's not going to be pulled out of the model. So we see here 7.14 or 1/6 is what's happening in this lower axial brace. That's as much tension as we're experiencing right now, just from these compressive 100 kips at each floor level. So that's what we're seeing in that brace. So what we want to do is kind of get ourselves enough tension in there to overcome that 7.1. So let's say 7.5 kips is that's what we're going to pre-tension these braces for. So once I go, let's take a look at this thermal loading and how we would do that. In the help menu, it gives us a nice formula. It tells us what the formula of the tension of the thermal loading is. But what we want to do is rearrange it. What we want to find out is how much temperature change or differential should we be applying to these braces in order to get the known quantity of that tensile force on that cable or that rod that we have in there. So the known force that we want is the calculated thermal force. We need 7.5 kips. So that's right off the bat, that's what we need to apply. In the equation, we also need to apply the member's cross-sectional area there. We also need to do the elastic modulus in there, as well as our coefficient of the thermal expansion. So you'll know this piece of information just from the member shape, and then from the material properties of that shape. You can just plug and chug, and what you're going to get there is a stress-inducing temperature of 50 degrees Fahrenheit. So what we want to do is take that and apply it to our model. So let's take a look at our model. I'm going to open up my model here. Let's double see here. So we should be seeing here. Great. So this is the model that we've been discussing. And in here, this is really just this 100 kips at each point there applied. What I've got here is these members, just these 1-inch V braces kind of coming down on there. And what I would do is just kind of solve that model, and I'll run it. And what we've got right now, these are not tension only. They're kind of going to be experiencing these members. Let's take a look. So yeah, they're both ways. So what we look at there, we just kind of confirm what we saw earlier there is at 7.11 approximately there. So what we're going to be trying to do is pre-stress that so it's 7.5. So what we'll first do, let's take a look. What would happen if I take those members, I'm going to switch them over to be tension only. And so I'm just going to tell the program here that these are tension only members, and I'm going to rerun the model. So it ran okay, but if we run it now with just these gravity loads, what happens is that it doesn't converge. P delta has a problem, and the model will not be stable. It's not converging. It's because when it goes, these members are tension only, and that we said here, what we're applying is those compressive forces. Those are all going into compression. They're being removed from the model. So we can't just run them in and go from there. But we can do is that thermal loading to pre-stress it. So I'm going to go back and I'm going to apply that. So I'm going to go ahead and say I'm going to go to the distributed loads here, and I'm going to apply this as a thermal load, and I'm going to tell the program negative 50 degrees Fahrenheit, and I'm going to apply it directly to each one of these braces. And let's go ahead and click, click, click. And then what we'll do is we're going to run the same load combination, solve it. Now it runs, okay, we're getting those to be tension-only members. It runs, and let's quickly take a look at the bottom there. So what happened is that really kind of did a wash on the bottom level there. Those braces now have zero axial, so they're really just kind of being pulled out. You see there's zero bending check. So that 7.5 sort of gave me exactly what I needed to sort of let the model run, but it pulled the lower level right out, okay? And so the other ones here, they are still in there. So they're now actually showing us some of the tensile forces, and we've got that for the top two levels, and then we're going to see a different higher number here. So maybe 7.5 is a little light. Maybe you want to even go higher so that these lower levels stay in the model. But that's sort of kind of the idea is basically is we're adding that tensile force there and go from there. Let's get back to here. Okay, projected load is another one that kind of confuses folks a lot of times. So if you're living in snow country, you probably already know this, but if not, maybe you're like in California where we have snow country real close by, but we don't know it off the top of our heads a lot. Well, a lot of times projected loads are talked about for snow loading. The idea behind that is that the snow falls from the sky and it goes over an area, okay, but it's not going to be increasing as a slope of a roof, or as that slope gets higher, the member gets much longer, so the rake distance of that member is very long compared to the overall acreage of where the snow might fall. But the snow doesn't care, okay, it's just coming straight from the sky. So what the IBC does, and a lot of the building codes for years have done, is given you a projected load for snow. So 100 pounds per square foot might be a common one, but that's actually a projected load, okay? So what you're looking at, no matter how steep your slope of your roof is, it's really 100 pounds per square foot. So let's think about how that affects your model. So the projected load, if we tell the model it's 100 pounds per square foot, for example, what we do is we take the applied load of 100 pounds per square foot and we multiply it by the member's length in the horizontal plane divided by the actual member length. So this is easier to see once we think about this and how it would be laid out. So we take that 100 pounds of distributed load, and if we were to apply it like a dead load, for example, we would just apply it vertically on that member, and we would see that that would be actually more here. That would be 14.1 is the distance from the top boundary condition to the lower boundary condition. So this is a longer member than the 10 feet. So for ceiling tiles or, shingles or anything that you're applying as a dead load, yes, that's a longer load. That is per square foot or per of that member. But for a snow load, what really happens is it applies it kind of over that distance of the sky or the acreage of coverage there. So that number changes, and so what we're doing is we're just basically converting it from 100 times the 10 feet, which is the distance horizontally, divided by the actual distance, okay, or the actual member length, 14.1, and that comes out to be about 70.71 in this example. So the program, when you say, I want 100 pounds projected in the PY, what you're really getting is 70.711 applied on that along the distance. Now, the big piece, too, to note is that you are getting less load, and that is what happens. What the IBC is asking for you to do, but you don't want to be surprised thinking that you should have gotten that 0.71 on each side. Look what we see that the boundary condition and reactions show here. On the right side, we have 0.5, so it's a little different. But you will be seeing the display of the load, so it's really nice to be able to verify that visually once you've applied a projected load, what it comes out to be. Okay, so point loads is the next topic. Point loads here, as I mentioned, can be basically are identical to joint loads, except they just don't have the joints. You can apply them along anywhere on the member. So they can be applied in the global axis, X, Y, and Z, but they also can be applied on the local axis because a member has a local axis. So that's what we're associating that local axis with. A joint load doesn't have a local axis, okay? It can be anywhere. So that local axis, so this helps you apply maybe something perpendicular, like this is a local little y, there we see. And we can also apply moments about the member's local axis. So you're always helpful to display the local axis. I always like to do that. You also can do the torsional moment about the local x-axis, and so we can kind of see that showing here as well. So you've got the ability to apply point loads to the members in all different ways. The next one is area loading. So area loading can be real helpful when you're applying it to a structure, maybe a building structure, and you want to apply it as a polygon. It can be 3 or 4 sides. We can define an area, and the load will be applied underneath that area. The loads are applied to members and walls, so it's either one, members and walls, and you can also apply it as a one-way or a two-way load attribution. So the key here is that this is a load attribution. I'm not talking about design. I'm talking about one-way or two-way load attribution. A best way to kind of describe how the program works is that it takes, if we look at these 4 points and I'm applying this as a one-way, it takes that and divides it in half. And so half the load goes to the lower beam here, half the load goes to the upper beam here. And internally, the program breaks these up into little triangles. And each one of those triangles here gets a little point load, and that point load gets distributed back to that beam, and when we basically make a meshed smooth load as a distributed load onto the member. That happens for both members there. You also see that for a two-way. A two-way takes that same 4 points. You define those 4 points, and we'll talk about that in a second, but you define 4 points or 3 points. In this case here, what we do is we take just basically break it into 4 segments or triangles, and then that also gets broken into little triangles, and that gets distributed. So if you're doing this by hand, you might kind of imagine, okay, yep, that's like a triangular loading on there. This is just if I was just going to be a hand calc, I would take half the tributary area, apply it to one beam, apply it to the other. Same kind of thing here. We're doing a two-way load distribution onto these members. Okay, now a lot of times we're smoothing that. We take a smoothing algorithm, but if you want to work with how little these pieces get, so maybe it's a real tight, nicer mesh, and it's a lot smoother, for example, you can work with here inside of the global parameters we have in the solution an area load mesh size. It defaults to 144, which is 12 by 12. So nothing's going to be bigger than a 12 by 12 square or triangle, basically. But what happens is you can take this number down, maybe to 12 inches. Below 12 inches, I've watched models kind of slow down, because if you imagine internally, we're breaking them up into little teeny pieces, and so you can kind of grind your model to a halt if you went down to like 1 inch if it was a bigger model. So 144 is always a good number to start at, but if you are wanting to look at your area loads, you can sort of work with this number here and make it a little smaller. To apply area loads, some folks get confused sometimes. It's pretty easy, but we did make it in a way that was so that you can do any shape and you can apply it in any direction. So sometimes, you know, we want to see which way we can apply it. We have a picture here. We have it A, B, C, and D. And what that indicates is the click of your mouse. So your first click where you identify what this area load is would be A. So your first click would be here. I'd be drawing. My second click would be above that. My third click would be on the right up here, and my fourth click. So you can go in any order. You can start up here. If you started up here in the right corner, it would be A up there, A, B, C, D. Okay, so it's however you start your clicks is where it indicates that. Now, when you choose, once you've clicked all this, you'll choose whether you want to be going in the AB direction, BC direction. So that's how the load will attribute to the different members underneath it. So the A to B, for example, would mean that the loads would go to the top member up here and the bottom member down here. The load would be attribution would be going in that direction. Okay, so A to B, if that's how I identified it, that's the load attribution. If I said I wanted to go in B to C, it would be taking the direction of this B click to my C click. So that's the load attribution in that direction. I can also do perpendicular to C to D. So that means it's going to go perpendicular to this member right here. So you have a couple different ways to do that. The other thing we do once we actually create these area loads is we create transient area loads. And one of the things that's nice about the transient area loads is what those are is really what the load got distributed on the member. So once we've created the area load, once you've just identified the direction of that area load that you want to apply it to, and run the model, you'll see that there pop up in your basic load cases spreadsheet a transient area load. Let's take a look at how that works. I'm going to open a model, and I'm going to just take a quick look at it here. Let's see. Tab. Oops, there we go. And we're going to clear results, sure, and say nope. Okay, so in this model here, I just have 3 different bays of beams, and what I want to do is I can see that I have different area loads. I have a one-way area load in one direction. It's applying it in the X direction here, just indicated. What it's nice about the program is that you can get this little arrow. So it shows you, even if you might have messed up, you can see it visually, which helps you really identify which way the loads are going to be going. So you have this one here is going what we see in the X direction. I have another one here that's going in the Z direction. Being applied. These are both one-way. They have the arrow that's one-way direction. The last one I have here is a two-way flat. So that one's applying the loads in 2 different directions. Okay, so what I want to show you is I'm going to solve the model here. I'm just going to solve it for a one-way. And so when I solve that single combination one-way, okay, this is actually my basic load case 1, the loads get distributed to the members, to this upper member here and this lower member right here. And I can verify that by looking at this transient area load. First of all, you can just verify, yep, it went into my basic load cases spreadsheet. There it is, and there are 2 basic load cases that were created that created this from this area load. But the best way to do this is visually represent it. So what we're going to do is let's go and see that, how it works. I'm going to look at this in isometric view, and I see that the loads got applied here to these 2 members. So solving an area load one way applied it to these 2 members here. We can also apply, let's run the second one. which was right here in the Z direction, and it was going in the other way. I'm going to say solve and run it again, and let's just quickly review that one again. So this one is applying the loads in the other direction, in the Z direction, and it created a transient area load that shows us that it applied it to each single member on here in the transient area load. So it distributes it to those members. Now the reason why you only got those two members going in the other way was that there was no members in that direction of the load. So here in the Z direction, we actually have little members or joists that are there to receive the load. So the load that is the one-way load actually won't just go to the outside members. They'll go to anything in the interior of that area load as long as it's in the direction of the load that you've applied. So the very two different ways, and we can see that we'll run a batch solution here. Let's just refresh our memory. So batch the solution. And so we see, so this one was only for two different members because those were in the direction there. And then these were for the other, each one individually. And then lastly is those two-way. The two-way distributes it basically to every single member in that area. And what we see there, we get that showing here kind of this triangular loading. And what's happening is each bay has that X that's drawn internally, and those little point loads are being attributed to each member in this bay for a two-way distribution. So you have a lot of different ways to apply that load in an area load. Now, the way you would sort of decide that, you would just say to yourself, okay, do I have a metal deck? And the metal deck spans in one direction, and so that's how the loads get distributed. Or do I have maybe a concrete slab and it's going to distribute it in two ways? Maybe wood decking might be a different, maybe one way, and how does it span? So you can kind of make those decisions as you, depending on how the loads are really going to be transferred to the members below. Okay, and the last here I also want to show is for before we leave area loads is surface. We also have open structure type of loading. So the open structure is still a projected area load, and what it does is it projects it based on the surface area of the member. So this one in particular, so we draw it just like we would have drawn a normal area load, but we tell the program it's a open structure, and it's as if here it's taking a look directly at that member that it's underneath it, and it says that's a HSS 4x4x6. The width is 4 inches, and that's the projected surface area that the wind is going to be blowing through here. For example, a lot of times open structure is going to be wind load type of structure loading. So you can see here 4 inches. You calculate that 4 inches. Take maybe 20 pounds per square foot, per running foot there. Multiply that. Sorry, this is per square foot. 20 pounds per square foot of load. Apply it to 4 by 12 inches there. You can see you get about 0.66 pounds per running foot that's going to be applied to that one member. So we're not looking at the full area below the structure of where that area load was applied. We're just looking at how much of that area gets hit across the surface area of the member. So if that's not a 4x4, if that's a 8x8 tubular shape, then it's going to be, this will be an 8-inch number right here to calculate this distributed load. So a big note here is that braces don't get area loads. So in this case here, we're going to see, you're going to see in a second here, the loads don't go to the braces, but also there's no shielding. So as I blow the wind through there, I'm going to see that the front face actually column in this scenario gets wind. The back column is also going to get wind. The beams are going to get wind. The braces are not going to get wind. And we can see that here in a second. So right here on this right, we see the columns get wind as we blow wind through this in this open structure type format. These braces do not get it. The beams as well get it. So we see that point, this is a 6 pounds per running foot, which is the number I calculated. I think we have some other shapes in here besides this tube shape. We have maybe some angles and some other stuff like that, so we're seeing that as well, calculated and applied to the structure. So open structure is a helpful tool if you're using maybe a lattice tower like I'm showing here. The next type of loading we have is going to be applying to plates of surface loading. You can apply surface load, which is basically just an area load, just like an area load, a constant pressure. It's going to be a magnitude. You tell the program the magnitude and the direction. The direction is going to be in the global X, Y, and Z, just like we've seen previously. The local X, Y, and Z as well you can apply to the plate. And then we can also do a projected, just like we saw projection in a beam or a member, a projection can be on a plate. So you choose the actual projection axis, and then it will project that load there just exactly the same way based on the projected area or maybe acreage, or however this is just demonstrating. Similar things could happen. You can use a plate for a roof structure, and you might be able to use that projected area as well. Thermal loading happens just like on a member, so you can apply that same calculation or equation we saw earlier to a plate, and you can apply that there. I'm going to show you an example of a tank and how a tank might work. So let's take a quick look at a tank. So let me open up my RISA-3D and grab that. We'll say yes. So in this tank, I just want to show you kind of a plate model. I just built a simple tank, and I'm going to show you, if I use my quick buttons here, I can show you the local axis of this plate. Each single plate is being entered in here, showing us the local axis, X, Y, and Z. And what I might want to do here in a plate model would be to apply a surface load. So what I can do there is just apply that by clicking on the Apply Surface Load to Plates. And in this case, a Z, a local axis, is really helpful. We can, if you're maybe this is a fluids tank there's actually something being loaded at the inside, and we want pressure to be put on each plate going outward. Maybe what we would do is we would use would be a positive, maybe let's say 0.05. Apply that directly, and we can say apply to all selected plates. And we zoom in here, we see that it's a pressure that's going to be positively applied from the inside out onto each plate. If we look down on the structure here, we can see that a little bit better. So these are applied internally and then applied to the plate. You can do different things. Global, you could even, I guess if you're talking about maybe wind, applying the global axis might be helpful on a tank. But usually local axis comes really nicely on a tank. And the local Z-axis is very helpful. Okay. So the other thing we can do is with wall loading. So I've mentioned wall loading as we've gone around, but I want to kind of talk about all the different options you have for walls in one area here. So in the wall panels, what we see is that you can apply a surface load just like you can apply a surface load to a tank like we just saw, but it's a little bit different. It's a little bit more flexible. It allows you to use lots of things like the full wall or just partially of the wall. You can apply a constant or a tapered force. You've got a lot of control on that surface loading, and we're going to see that. I'll demonstrate that in a second for you. You can also do distributed loads. Like I mentioned, you can do those to the edges of the walls, a distributed load to the, maybe the roof structure's framing in, and we can put some distributed loads on there. Joint loads can happen in the wall, and they can happen anywhere. So anywhere there's a joint that coincides with the wall, not just the corners, but anywhere there's a joint, you can apply it, and that will be a point where the wall will mesh to that joint load. So that's a really powerful tool if you need that. And then you also can even do area loads. So let's take a look at a model. I'm going to jump back into RISA-3D quickly here. I'm going to go to a wall example. And we'll see here. So if I open up RISA-3D one more time, I'm going to say no. Okay. So in here, this is kind of just a sample model I built just with a wall to sort of demonstrate, but I wanted to make it more like a building structure. So I put some other stuff in here so we can do more three-dimensional. But this wall here, I want to show you a little bit, a couple of the things I just mentioned. So first thing is the distributed load. We can apply that wall distributed load, maybe a -1 in the dead load might be a case where we put the distributed loads on there. And I'm going to just say apply it to that edge, and I see that it applies along that entire edge. That could have been tapered. I could have changed the locations. I can do all sorts of stuff like that. The wind loading might be something that you use surface loading for. So there's two surface loading buttons. One's apply surface loads to plates. we're going to use the one here. It says apply surface loads to wall panels. So if I click on that, I'll see here that I can apply that maybe in this model in the Z, capital Z direction would be helpful. We apply surface load there, and I can apply it in maybe, let's start at 0 location and go up to 13 feet. And then let's taper it. So it's top magnitude, which is the top location. That's going to be maybe negative, or let's say, let's do negative 0.02. And the bottom location is going to be negative 0.018. Maybe some small wind load changes along the way. And we'll say wind load, and we'll just click on apply it. And we can see it tapers it, and it doesn't go the whole way up. I kind of landed right where that parapet might start. So what I want to maybe just do is, do some constant parapet loading. So we'll go back in there, and we'll say 13 feet all the way up to 15 feet and negative 0.2 to the top. So we have kind of 2 different types of loading on that structure. So you've got wind loading. The next one maybe is some live load. Maybe we'll just do some area loads for the live load. So what I did do in this model, let's go ahead and just show that there. I put a little beam in here. It's just a false beam. If I want to use the area loads, I do need to have a beam along the edge, but once I do, it will connect to the wall just fine. So I just put like a little dummy beam, a 4x4 to help me collect this area load, and I'm going to apply that to my structure. Maybe just a vertical Y, and we'll just say this is going to be maybe negative 0.5 and A to B, and we'll call this a live load. Okay, so A to B means I want to think about my clicking. So A, B, that means that the loads are going to go this direction, and I'm going to say C and D, and I can verify that by the way that the arrow points. So I have A to B shown out there, and we'll verify that as well once we run the model. The next one I'm going to do is I'm going to do some earthquake load. So I want to just show you a little bit about how this one will work. I'm going to put a joint kind of anywhere. So we'll see how that works. So to put a joint, I'm just going to actually just draw a member, like I'm trying to draw a member, but I'm not actually going to draw the member. I'm just going to start it. And what that did is it just dropped a joint in there for me. And what I'll do now is put a joint load right in there. So we'll say this is going to be our earthquake load, and maybe like a kip in there at that funny load there. But maybe let's put some bigger ones in the top where maybe the rest of the structure frames in. So I can put that in up here. So you can put joint loads anywhere, which makes it nice. And I've got kind of a collection of different loading. We see that again here. I've got those. If we wanted to change it by chance, if there was anything that we wanted to do, one of the tricks here, if we click on that, it's going to a plate. We can click over the wall panel, see, and we can just make a quick modification in here. Oh, whoops, we forgot, or something like that. We could adjust that. But it also just helps us to see, we use those categories that we were talking about earlier, and what we'll want to do is run this model, because I want to show you how that model gets plated once you have loads on it. So the load combination spreadsheet, I'm going to open it up, and I could kind of define my own load combinations, but I want to just save some time, so let's use our load combination generator. As I mentioned, this is a great time saver. So I'm going to go into the gravity tool here, and I didn't apply any of these types of loads, so I'm just going to say generate and not have them checked, and I just get some dead and live load. I'm going to go over to wind, and I'm going to pick the 2D one because I just used WL. That was important. I used the WL, so I'm going to say generate, and I'm going to go over to seismic, and I'm going to use the 2D only and generate that, and now close it. So one of the things to mention, if you're not familiar with RISA load combination generator, it is only present up here in red when this load combination spreadsheet is open. So if you ever lose it there, just pop open your load combination spreadsheet and you'll see that big button up there. So it's kind of one of the ones that comes up only when you're viewing a load combination spreadsheet. Okay, so when I have all these combinations created, I'm going to just solve a batch, run through all the different load combinations I just created, and first thing I'm going to do is show you that transient area load. So it did go, I'm going to turn off my grid, it did go to the wall, which is nice because that beam was there. Had that beam not been there, it would have all gone to the back beam instead. So we did want to distribute it, and so I put that dummy beam in there. We also can see here, let's take a look at how the wall panel meshes. So I'm going to look over to the panel spreadsheet here, our plot options, and I'm going to show the mesh. And I'm just going to see here, but let's turn that off there. There you go. So if you see, I'll turn it on and turn it off. But each single location there got meshed to this wall panel, so that that distributed load is going right into the plates there. Kind of hard to see it when it's showing, but you can see when I turn it off, just unselect it. Now you can see that that is exactly what's happening up here. These are getting smaller because it's trying to mesh in this area. So that's a really nice thing to see visually, that you're applying that load and it's going right into the mesh of the wall. The other thing we can see too is by going on to this plot options, I'm going to go over to the loads, and we have some transient wall panel loads that get created. So when we blew that wind on that into the page, a lot of times people ask is what happens with that opening? And if you look at that, what happens in the opening is that the loads get distributed to the wall, but they also get, anything through that opening gets kind of assigned over to the edges of the opening. So it's basically just pushing all the load into the edges of that opening and point loading it there instead of just dumping it right through. So we don't assume that this is open. We assume that that is probably going to have some glass, and so the load's going to get to the edges of that opening. So you've got kind of a different type of way to see it. That's not quite obvious. If you go to the Loads tab, you'll see that there's ways to turn things on and turn things off. So you can show magnitudes and just display things differently. So that's kind of all the things I wanted to show you on this wall panels model. Let's jump back in and take a look at moving loads. So moving loads is a way that you apply loads to a structure. Maybe if you have an industrial or a crane type of structure where you can apply it to moving along the structure. Now, what we've got here is it's a two-step process. The first step in that process is to define the moving load pattern. So you're telling the program what is the pattern of this moving load, and what is the magnitude, the direction. We'll make one coming up here in a second. So we'll see all that you have to put in there, but you want to do a moving load pattern. And then once you've defined that pattern, we're going to want to apply it to the structure. So we're going to tell the program where it should be applied to, which nodes specifically is this load going to be moving along. So let me open up a moving load model here. I'm going to jump right in and go into this. Let's see here. So let's clear our results. Sure, we're going to continue. And we'll see in here this is going to be kind of a funny shaped structure. But what we're really trying to show you here is like a crane moving across this, I don't know, kind of framework, and or rail. Lots of folks ask for rail loading, things like that, and that's kind of what we're looking at here. So what we've got is we're going to start with that moving load pattern. So I'm going to go up into this icon here. It says View, Edit, Moving Load Patterns. And I'm going to create a moving load pattern. So I'm just going to say Add a Pattern. And by the way, you have some of the defaults in here, some kind of truck loading and some transportation loading ones here. But what I'm going to do is create my own. So I'm going to say Add a Moving Load Pattern, and we'll just call this Load. Let's call this Load Webinar. Load Webinar. Okay, now we can tell the program first what you want to do is we look at this picture. It's a load 1, and we want a magnitude, so maybe 3, or let's say 3, it's starting out, and a direction. So the direction we want to say is vertical Y direction. Now I did -3, that means it's going to go down, and that's the first load. It doesn't have a distance because that's the first point. Now, the second point, if we think about maybe like a truck, for example, the first set of wheels would be your load 1. Your load 2 is your second set of wheels. So we'll maybe say this one's going to be a -3, and that's going to be a direction Y. But how far back is that than the first load? So I don't know. I don't really know that much about the truck, but let's just say 6 feet. Okay, so it's going to be 6 feet behind there. And the next one is we'll say maybe this is a little larger, maybe 5 kips. Vertically in the Y direction, and this one's going to be a little bit farther back, maybe 8 feet. Okay, so but you can keep on going, making all these different types, keep adding these. I'm just going to do 3 different loads, and I defined it as Loads Webinar. I can say OK, and I'm going to go, and now I see that it popped into there as Loads Webinar. So that's all I have to really do is just add it to my database, on my library. I'm going to say Close. and then I'm going to open up my moving loads spreadsheet, which is blank, and I'm going to define it in here. Now, before we define it, let's turn our nodes on so we can just see what the numbers are. Let's see, and we're going to just rotate just a bit so it makes it easier for us to see things. Okay, so if we go into our moving load spreadsheet, I can just click in there to start a moving load, and it'll just be a tag. We can leave the tag as M1, that's fine. The pattern, though, we do want to pick out what the loads webinar one is that we just created. The increment, so how often are we going to be applying this moving load as it goes across our screen? 1 foot seems pretty reasonable. If you have something really small, you might want to use a smaller increment, or if you have a really long item, maybe you use something like 2 feet, every 2 feet apply it. It can go both ways, so we can apply the loads in one direction, and then it can turn around and go the other way. So the first joint here, I'm going to tell the program is going to be N41, which is this lower left corner. The second joint here is going to be N40. The third joint is going to be N39. And what I'm doing is I'm just sort of working around this, and wherever it sort of turns or becomes a different member, I'm going to just identify that. So N38, and it's kind of hard to see there, but N38 is the next one. And then the last one is going to be this top here, N37. So once I place that N37, oops, there we go. I've got it in place. Before I'm finished, the last piece you want to do, so you have we've identified the pattern, we've now created a moving load, and then you would want to make sure to go into the load combinations and create a load combination with using this M1 as a basic load case. So you want to put that in your load combination spreadsheet, just like you would in any other load. Okay, so then now it's in my structure, and it would be loading it that way. So to visually verify that, just how this works, so the great way to do that is to look at it in our plot options, and you can go over to Loads tab. You'll see in here, you can see by animating the moving load or load combination. So I'm going to animate the moving load, and you can see on the lower portion of my screen, you should be able to see, let's say okay, hopefully everybody can see this, is that it's animating across my screen. So it's going to be, you can make it go faster, and as it goes faster there, we can see it's going to go up, and then it's going to turn around because we told the program it should be going both ways. So that's the second cycle. So this is really what the increment is applying it to the model. As you run the model, you'll be getting each one of these loads applied to the structure. Okay, so very cool. I love seeing the actual animated. That makes me realize I did it right, and kind of fun to see on your screen. Okay, so that's your moving loads, and the last load here, I'm a little over in time, but I want to just make sure we get into the last piece of loading, which is automatic load generation. Building design here can be done. This is specifically meant for buildings with rigid diaphragms. If you have a rigid diaphragm defined in your model, you can do automatic loads for the wind and for the seismic. So if you take a quick look at that, the way you do it is, and I'll show you in a second how we do it, how we insert it, but all you have to do is define the parameters of the wind. So you tell the program what code you're using, you tell the wind speed, some of the factors here. For seismic, you also do the same thing. You tell the parameters of the seismic code that you're using, and then you'll look up all your parameters for where the geography of that building happens to reside, what would be SD1, SDS, and all this would be right from the building code or from, you just call the local jurisdiction and find out. For the seismic and wind, and then it will automatically apply loads for that structure right into the rigid diaphragm. So this picture helps us see that you get a point load right into the rigid diaphragm. And I'm going to open up that model real quick here. So if I open up the rigid diaphragm model, I'm going to tab over there and say yes. Oh, we'll say no, sorry. There we go. So this is a model here that I have created. It really is just addressing the lateral system. It's just concrete walls and moment frames, and it's not addressing any of the gravity system, just the lateral system. So what I have in here is rigid diaphragms defined. Rigid diaphragms are really easy to work with. You just put in one node, tell the program that one node, that the entire plane has a membrane rigid diaphragm on it, and then it's going to be rigidly connected along that entire plane. And so when doing that, we also have the ability to apply these automated loading. So we can say insert wind load, and we get that, what we saw, that wind load parameters on the top there with the different ability to set all those parameters. And then below here, once you calculate the loads, it gives us a breakdown per floor level or per diaphragm, what the loading, what the actual, well, this one looks like what we're going to tell us is the width and the length, and then as we scroll down below that, what the force is going to be at each one of those diaphragm levels. So you're just seeing an echo of that information up here of the code information, and then it breaks it down into actually calculating the force for you. So when we're working out in the field, I would want to probably print this out, keep this with my hand calcs to check in my calc package. Similar thing I'll see here for the seismic. If I go to insert seismic load, I will also see in here, I get the seismic load applied here with the code, give it the parameters, then it gives us here a calculated period, the method that was used, and the base shear. It gives us the governing equations, and as I scroll down below that, I get very similar here. It's going to give us a height of each diaphragm with the weight. Then it gives us a force in each direction, forces in the X and the Z directions, and then we scroll down and see a little bit of the actual different directions, length and width of this diaphragm. So if I can also print this out and have that with my calc package. And what I can see visually on the model now is also, so I have some dead loads on this as well, but I can see the wind loads right applied directly into the model. So if we look at this let's look at it from the side, and we can see that it's actually doing a really great tool. It's doing wind load in the X direction and the Z direction, but then the partial X directions. So we're going to get a lot of different loading in there, as well as the eccentric loading for the earthquake loading. So you're getting a long list of different loads being applied, and I scroll down the structure, and it sort of alternates for me as I see that there, and it's going right into the diaphragm. And if you look at it sort of down from above, what you're looking at is it's kind of scrolling, it's going right into the middle of nowhere, or the center of the structure, center of mass there. So it is, but that is all connected because of that rigid diaphragm. You can also view that right in the basic load cases spreadsheet. So we see again those grayed out numbers, and you can click on any one of those. Now these are all gray because the program doesn't really want us to alter those because they're being calculated from that insert there, that menu over there. But you have the ability to take a look. You could even copy these out and work with them as on the side if you needed to. But you have the ability to really work with all of these inside your basic load cases spreadsheet. So that's been all of the different types of loading that we have in there. We've kind of hit a lot of different topics, and hopefully if people have questions here, we'll be able to answer some as we go on.